Thanks, Jerry. It's always tough being first after lunch. That very nice lunch that we had, thanks to our sponsors, is starting to kick in, and I hope I can entertain you and stave off the sleepiness that comes after lunch. So today I'd like to go through quite a lot of material. 20 minutes is not very much. I'm going to go at a pretty high pace. The material should be available for you after the conference so that you can go through at your leisure and look at the details that maybe I didn't get a chance to go through in detail. So what I've done here is I've taken the actual block diagram that we're currently using in the working draft. And you can see it's pretty complicated. There's a lot of blocks there, but let me go through. There are basically 4 big blocks that we've got: input formatting, BICM, framing and interleaving, and waveform. And I'll go through where S32-2 works. One of the ad hoc groups that I'm the chairman of is the S32-2. So about half of that, and I'll try and get through that as quickly as possible. My colleague Najib will talk about the other part, S32-3. What status are we at? I'm very pleased to report that in S32-2 we're just about done. We have a current working draft that's available for ATSC members. We're up to revision 4, and at a hand-waving percentage, in terms of S32-2, I'd say we're almost 90% of the way done there. Overall, we've still got a long way to go in terms of some of the other sections, but we are pretty much finished there. A lot of green ticks, and within the coming month or so, I think we can get everything finished in S32-2 there. So first of all, let me go through the baseband framing. That's the input of the file layer part. We do have a couple more blocks that are handled within the S33-1 group, looking at the layer 2 there. But in terms of layer 1, baseband framing is where we start. And that takes generic packets from the layer 2 and maps them onto the baseband frame. Baseband frame, we can consider this as a kind of layer 1 packet. It's a very simple operation with a very low header there, about 2 bytes per packet. And the actual frame length will depend on the modulation and coding, but of the order of several thousand bytes. The BICM block, I think, is one of the main engines of the physical layer standards. BICM stands for Bit Interleaved and Coded Modulation, and that consists of 3 major blocks, sub-blocks: the FEC block, the forward error correction, which provides us with our robustness, bit interleaver, and the mapper, or mapping those bits to constellations. We have in each RF channel up to 64 physical layer pipes, or PLPs. And we've decided that for each service, each group, we'll have up to 4 PLPs in that group. So even if you're sending one particular service, that can have multiple levels of robustness. So in the next few diagrams that I'm going to go through, you'll see lots of different operating points that you can use. But what I'd like to emphasize is that it's not just one operating point per RF channel. It's multiple operating points for the same service that's possible, and up to 64, in fact. So if you have a channel that's shared by either multiple services or multiple broadcasters, you have an almost infinite number of possibilities there in terms of where you want to position your service in terms of robustness and efficiency. First, the FEC codes. We mentioned this, if you were here at the boot camp last year, we mentioned about this. We do have very good status on the FEC codes now. It's pretty much done and dusted. We have 12 code rates, which is an incredible range from 2/15, which is 0.13, to 13/15. If you're not familiar with this area, the code rate is basically the ratio of the information to the parity. So a 2/15 code rate has a little bit of information and a lot of parity, very robust. If you're at 13/15, mostly information and a little bit of parity, not so robust. So depending on where you want to position your service, you choose your code rate. We have 2 code sizes that are available. 64,800 bits is basically our high-performance code that we expect will be the main code used. We do have another alternative code length, 16,200 bits, which will provide low latency and less complexity if that is needed. The information and payload is protected by two kinds of codes, outer and inner. We'll get that onto the next page here. And if my clicker can work. Luke mentioned this morning the two structures. This is actually very unusual. Most other standards, in fact all the other standards I know, only use one particular code structure. But because we've got such this large range from very robust to very high efficiency, during the standardization process we found that not one particular code structure would be suitable for all of those that high range. So we've chosen two different structures there that give us the best efficiency in both worlds. In terms of the outer coding, we have several options. We have BCH, which will give us error detection and also 12-bit error correction there. We also have a couple of options there, CRC just for error detection, and none to give you that little bit more efficiency if that's what you need. The bit interleaver, the next section. There's a lot on this slide, but I'll just go to the highlighted bits here. The bit interleaver is basically optimizing the combination of the code rate or the FEC code to the constellation. And in the next slide, I'll go to the non-uniform constellations, which is a big feature of ATSC 3.0. So we've tried to optimize every single part of the BICM chain, not only the FEC codes, not only the constellations, but everything in between as well. The mapper, the constellations, we've basically done a huge range of constellations here. Of course, we start off with QPSK, and then for the 16 QAM, 64 QAM, 256 QAM, 1024 and 4096 QAM as well. They are all non-uniform constellations. And this is a very new method of mapping, where rather than having the same constellation being applied to every single code rate, we've optimized the constellation for a particular code rate. So if you can imagine a very robust code like 2/15 operates at a much lower SNR range compared to something like 13/15. So that means because of those operating ranges or the operating points are quite different, the constellation, the optimal constellation is different. And that's what we've done, and we've gotten very close to the Shannon limit because of that. And you can see here there's a similar graph to what Luke showed this morning. We can gain about 0.23 at 16 QAM. For something like 256 QAM, which would be a regular operating point similar to what we're using in ATSC 1.0 today, we can gain around about 1.5 dBs just by using that. And that's significant. That's very significant. What will happen, and if you look in the material, I'm not going to show it to you today, but if you download it later on, I've got all the pictures of the constellations, and they're very pretty. So I think this is going to be one of the prettiest standards that we've ever made. The actual constellations themselves, especially for the lower coding rates, you'll see they tend to be more PSK-like, rounded, rather than the square constellation. So that's another feature that you can look forward to in the standard. Very well optimized. So putting the FEC, the bit interleaver, and the mapper together, what do we get? We get these capacity plots. I'm going to go through quite a number here. The first thing I want you to notice is that there are a huge number of operating points. And not just one operating point per channel, multiple operating points per service, and even more per channel if you've got multiple services per channel. Basically, in AWGN, you can see we're very close to the Shannon limit here, range of -5 to 30 dB. In AWGN, the maximum is 60 megabits per second in 6 megahertz. So a huge amount there, though that does take 30 decibels there. We do need a high SNR. For the shorter code of 16,200 bits, we've limited the constellation size to 250 QAM in that case. We go up to about 23 dBs in AWGN, which is about 40 megabits per second. I'll just quickly flip between these two slides, and maybe you can just see that in the shorter code, we're moving a little bit further away from Shannon, so we're not quite as efficient there. But we do get a couple of advantages here in lower latency and also less complexity. AWGN is more theoretical when we want to broadcast over the air and terrestrial. Perhaps the Rayleigh channel is a little bit closer to reality. This is the result from the Rayleigh channel, still very close to Shannon. We do need a little bit more in the Rayleigh channel, up to 35 dBs there for the highest points, giving us 60 megabits per second. Another thing you can notice is with the higher coding rates, the curves tend to flatten out. And that's a feature there. So if we're looking at having a highly robust signal, perhaps these coding rates wouldn't be used if in a Rayleigh channel there. Again, and this is the shorter code there. So many operating points. You know, how am I going to decide what to use? And I think that's something that's going to be it's going to be something hard for broadcasters to decide. So in the standard, what we've tried to do is to make a first approximation and say, these are the operating points that you are most likely to use in the standard. And we've made these mandatory. So you can imagine, and I think this is pretty much common sense here, if you look at the very high constellations, such as 1024 QAM 496, and the very low coding rates, that it's not a good match. So you've kind of got this diagonal, and maybe that's not going to, yeah, it's kind of hard with the distance. You've got that diagonal from the low coding rates at QPSK and then the higher coding rates with 4096 QAM. That diagonal is your sweet spot. We've gone from the maximum of 72 operating points for the longer codes to 48, and for the shorter codes we went from 48 to 28, I think. So we've tried to reduce that down. However, all of them will be available in the standard if you wanted to use them. Okay, so how does ATSC, this BICM part, compare to other standards? Luke mentioned this a little bit this morning, but you know, compared to ATSC 1.0, wow, I mean, it's no comparison at all. The use of LDPC codes gives you a huge gain compared to the Reed-Solomon convolutional codes used in first generation standards. And as I mentioned before, the non-uniform constellations give us another significant advantage there. DVB-T2, our friends in Europe have created a very popular standard over there, and you know, very recent, you know, devices coming out 2010. So you can see that we still have a significant advantage getting closer to Shannon there with ATSC 3.0. So we think we've done a good job here, even compared to the recent standards. Drilling down to provide a diagram that shows perhaps closer, these are 2-bit error rate curves. This is code rate 9/15 256 QAM, which is perhaps something that's very similar to the operating point of ATSC 1.0. And we can see that, you know, even compared with, you know, state-of-the-art today, DVB-T2, we're getting over 1 dB gain with this BICM chain. So kudos to all the people who've worked on this. I think it's a very good result. Interleaving is a very important part. We have both time and frequency interleaving available in the physical layer in ATSC 3.0. The time interleaver, there's two different types of time interleaving. The time interleaver itself, it separates burst errors in the time domain, spreads them out, allows the forward error correction to do its work there. In order to give the maximum interleaving depth, we've chosen to use a convolutional interleaver with single PLP, which means just one operating point over the whole RF channel. So if that's your business model, you can use a convolutional interleaver. It's very simple. It'll give us about 200 milliseconds interleaving depth. Of course, we do have options for lower interleaving depths to improve latency, and in fact, we also have the option of no time interleaving at all. We also have an extended interleaving mode for QPSK, which will double the depth compared to the other modes there. So lots of options here in terms of time interleaving. The multiple PLP, when we have multiple operating points within an RF channel, we have a rather complicated time interleaver. I don't have enough time to drill down into the details today. It's what we've called a hybrid interleaver, 3 stages, which consists of a cell interleaver, a block interleaver, and a convolutional interleaver. Basically, the block interleaver is the main engine here, which performs the intra-frame interleaving, but we do have the ability to spread the interleaving over frames via inter-frame interleaving using convolutional interleaver there. So we have, you won't lack for options in terms of time interleaving in ATSC 3.0. In terms of frequency interleaving, we have a frequency interleaver that separates the burst errors out in the frequency domain, combating multipath fading. It operates on a single symbol there. So both options are completely covered there in terms of interleaving. Just quickly, Luke already mentioned MISO. It's basically a pre-distortion. The MISO that we're using in ATSC 3.0 is a little bit different from that in other standards. It's a pre-distortion. It's specifically to improve the performance in 0 dB echoes in an SFN. It decorrelates the signal from multiple transmitters there. We have 2 options there, 2 filter lengths that can do that. Another option that we have is MIMO. We recognize that this is probably a future-oriented technology, but we thought it was very important to document this because perhaps the future is not as far away as it might seem. So we do have a lot of detail on the MIMO. I won't go into today because of time, but MIMO, the point with MIMO is that we need 2 antennas for transmission and 2 antennas for reception. So it's a big step, and we recognize that it may not be what broadcasters choose for the first iteration of ATSC 3.0. It offers a large number of benefits, including the trade-off between either additional robustness or increases capacity. The diagram on the screen there shows the increase in capacity there. So, if the capacity was what we wanted, we could potentially make the investment in having multiple antennas there to provide that gain. In the current working draft, we've standardized the 2x2 MIMO only. Vertical and horizontal polarizations would be the preferred implementation there. Obviously, there will be options for future extensions of MIMO. So in summary, what does all this mean? I've rushed through quite a number of points here, but you can get the idea that the ATSC 3.0 file layer is offering you, I would say, extreme flexibility. You're not going to lack for options. And so this means that not only are your needs going to be met tomorrow, not today, but they're going to be met tomorrow. You're going to have enough there that's be able to work for the foreseeable future, and hooks to allow for technology that we can't even imagine today. The state-of-the-art technology is implemented in the file layer. We have new state-of-the-art LDPC codes, QPSK and the non-uniform constellations. We have all the interleaving options, time and frequency, and several future technologies such as MIMO. So well covered, and definitely it is the way forward in the future for broadcasters. In summary too, we've just about finished our work. We have multiple operating points within the same RF channel, and as I mentioned, the points there of new LDPC codes, non-uniform constellations, and MIMO. So I'll end there and take any questions. Yes, Glenn.
Thanks, Lachlan. Great presentation. Just to get people really thinking, would you say a word about the interaction, the options between layer division multiplexing that was mentioned this morning, and the various physical layer pipes, and the the Shannon curve options that you were discussing this afternoon? How do those two relate? Okay.
Well, for LDM, for example, let's go back to maybe some of these. Where do I point this to? There we go. let me go back to one of the capacity curves there. For LDM, we've defined 2 layers. And as Luke mentioned this morning, here we go. Let's go back to the AWGN one there. So for LDM, we've got 2 layers. And the 2 layers are basically superpositions of the signal on each other at 2 different power levels. So we can choose 2 different points on this operating curve to operate at. We've got usually a robust layer and an enhanced layer. So we might choose, for example, something that's at 0 dB, which will, if you look on this curve, that will give us about 1 bits per second per hertz. And the way to look at this curve is you multiply the y-axis by 6. So 6 megabits per second per hertz would be at 0 dB if we used the whole channel for that. And you'd also get, for example, say you wanted to have another point then at 20 dB, or let's say 15 dB, which will give us about 5 bits per second per hertz. So 5 6s is 30 megabits per second. So we've got a robust layer of up to 6 megabits per second at 0 dB and an enhanced layer at 35 megabits per second available at the same time. Now that's just for the BICM. So we do need to think about the overhead for pilots, for guard interval, for bootstrap and so on. But rough figures in the air, that's kind of showing you what you can do today with ATSC 3.0. Is that okay, Glenn? Yeah. Yes. Last question. Okay.
Yeah, I kind of have a follow-up to that question. It seems like there's different ways to get different qualities of service.
Yep.
Either this layered division multiplexing you speak of, or the PLP option, more of a time division type thing. What's the trade-off there? Why would you choose one over the other?
Okay. That's probably going to take a little bit more time to answer, but it kind of depends on what service you wanted to do. Layered division multiplexing will give us that superimposition at the cost of a more complex receiver. To remove that, the actual how much we're going to lose in terms of that is in terms of the service that we need for LDM is still to be particularly quantified, but theoretically anyway, the LDM will always offer more capacity because we're superimposing the signaling. We have to also think about the coverage area because the 2, for example, the 2 power layers in LDM are going to mean that if you're limited for a certain power, then compared to the time division multiplexing, the coverage area will be slightly different for those 2 configurations. So you're going to have to then think about, what's my coverage area, and that may mean that you can't use exactly the same modulation encoding. You have to dial it back a bit, which will then impact your capacity because you're changing the power levels there. So maybe one simple answer to your question is the LDM trades off, some power there, which will impact your coverage area. And then to make the coverage area the same, then you'd have to change the modulation encoding, which would change your capacity. But it's not an easy, there's not one answer to fit, all sizes there. So you're going to have to look, what's my use case, what receivers are available, what do they do, and look at the actual, the numbers when they come out. But that's something that we're going to be working through as we get to the final specification. Okay, thank you very much. Out of time.